So say good morning. Say Happy New Year. Okay, so Happy New Year. Sit down. Okay, so previously we discussed about the enzymes in details, and that information, whatever we have discussed, like about the structure of the enzymes, the quaternary structure, usually it is in higher organization state, and how these structures determine the function of that enzyme. So keep quiet. So I don't want to. Okay. The main characteristics about the allosteric regulation or allosteric modifications. That time also we discussed about the hemoglobin. Okay. So here we will discuss. So how the changes in the structure will determine its function. So that is going to be, you will understand when you compare the structure of hemoglobin and myoglobin. So on. Second, the interesting thing is that you are taking oxygen in inspiration, exhale carbon dioxide. So oxygen is required for your metabolism, for all other activities, and whatever the carbon dioxide produced during metabolism, it is exhaled. So both the functions, which is very, very important. If there is lack of oxygen, difficulty, If there is excessive of carbon dioxide in body, that is also problematic. Okay. So these, all the functions are done by this hemoglobin. So you should understand the structure of the hemoglobin, and you can able to determine how it is there. Most of the topic about oxygenation, it is covered in the physiology. Hemoglobin, oxygen dissociation come? Not yet. Because subsequently it will be discussed more detail. So we will discuss here mostly about the biochemical aspects, the structure, and how it determines the functions. Okay. So first you have to understand the structure of the hemoglobin. Then you will, what are the functions, and then how you will explain the structure-function relationship. So 10 marks, very important questions. Explain the structure-function basis relationship of the hemoglobin with a diagram. Okay, so like that kind of questions will come, and you have to describe the structure, function, and all of the things. So first, so RBCs are there. You must have gone. RBC contains the hemoglobin. Okay. So this hemoglobin, there are 3 types of hemoglobins which are there. It is called as a HB. HB is a short form for the hemoglobin. HbA, HbA2, and HbF. So A, adult, second part which is there A2, and F stand for fetus. Okay. So it is a hemoprotein. If you divide heme and globin, so globin is a protein part, and heme is considered as a prosthetic group. Okay, prosthetic group in the similar kind of enzyme also. Okay, prosthetic groups and protein part. Prosthetic group is a non-protein part. So here it is heme is a non-protein part and globin is a protein part. So protein means amino acid sequence. Okay, so there are 2, alpha and beta. These are the 2. Globin means chains are there, chains of amino acids. Okay, So hemoglobin A contain alpha 2, beta 2. So there are 2 chain of alpha and 2 chain of beta. Hemoglobin A2 contain alpha 2 and delta 2, and hemoglobin F, that is fetus, contain alpha 2 and gamma 2. In a normal, if you take the blood and if you separate it out on electrophoresis, A will be around 97%, A2 will be on 2%, and F will be on less than 1%. Now why it is important? See, these chains are there, okay, alpha chain, beta chain. So alpha chain is common, and beta chain, like A contain beta, A2 contain delta, and this contain gamma. So only point to be noted here, that if there is a problem for beta chain, it is severely affecting. Okay. What problems that we will subsequently see. So if the beta chain is not properly synthesized, there will be problem. Okay. So in that situation, your A2 and F concentration will be higher. Okay. So that is the importance you should know about the percentage and the chains. So this chain, you should understand that A contain what, A2 contain what, and F contain what. Okay. So that is it. Now we will discuss mainly about the hemoglobin A. Yeah, anything? Hemoglobin A, so it is a conjugated protein. Heme is a prosthetic group, globin is a protein part, and both they will combine to form a hemoglobin. Okay. So it is a tetramer. It contains 2 alpha chains and 2 beta chains. As we are discussing about the hemoglobin A, tetramer, 2 alpha and 2 beta, and they form a quaternary structure. Okay, like you have discussed about the structural classification of protein. So what is primary? Sequence. Secondary? Folding. Tertiary? So what is the difference between secondary and tertiary? Both are 3-dimensional. That is quaternary. Quaternary contain domain. Correct? So what is the difference between secondary and tertiary? Both are tertiary, 3-dimensional. The difference is that the non-covalent interactions which are happening in secondary, they are very close. So how close? Yes. So nearby. So nearby 4 to 5 about it will be interaction. However, in tertiary structure, distant amino acids will be interacting, non-covalent will be. Okay. Provided in a secondary it is a hydrogen bond which is predominant, correct? And this one, so okay, whatever I do. So here also domain. So domain will be there in quaternary. So alpha 1 will form one domain, alpha 2 will form another domain, beta 1 will form one domain, beta 2 will form. So these are the domains. So it is a quaternary structure. Allosteric, that we will discuss. We know what is meant by allosteric. There are modifications takes place. Allosteric modification, it is complex and compact. This is spheroidal and it classified in the globular protein. Okay. If you see the structure, what is the structure of RBC? Concave. Okay. So that is there. So then we will divide it into hemoglobin into heme and globin. So first let's discuss with the heme. Okay. So heme, it is a ferroprotoporphyrin 9. Okay. So it is also consists of 2 parts. First is the ferro means iron, and second is the protoporphyrin. So it is a iron ring and the ferrous. So these are the 2 components which are there in the heme. Okay. That we will discuss extensively when we will discuss about the heme synthesis. How this, what is the structure of this protoporphyrin ion. So ion will be just added to this protoporphyrin ring, and then it will form the heme. Okay. So a little bit about this protoporphyrin ion. So what is the ion? So plus 2 it is a ferrous, and plus 3 is a ferric. Okay. Second, oxygen will bind to the ferrous +2 only. If it is a +3, it will not bind. Okay. Next, reduced form of iron is a ferrous. Oxidized form is a ferric. Okay. So that understanding you have to keep it in mind. So protoporphyrin, it is actually contain 4 pyrrole ring which are interlinked by the methylene bridges. So these pyrrole ring, so it's called as a tetrapyrrole. Tetra means 4, pyrrole ring A, B, C, D, and they have a substituent groups which is in the form of MV, MV, MP, PM. So this is also important because that only will determine this 9th series. So these are the series. Okay. M stand for methyl, V stand for vinyl, P stand for propanol. So if you see the structure, it is like that here. Okay. So the iron will be there in the center, and there are 4 pyrrole ring A, B, C, D. Each are linked by the methylene bridges. So this is called as methylene bridges, and they have M, V, M, V, M, P, P, M. M stand for methyl. This is vinyl group. This is methyl group. This is vinyl, methyl, propanol, propanol, and methyl. So this only the structure is categorized into the N series that we will discuss subsequently. But just to overhead. Now iron has how many valency? 6 valencies. Okay. So if it is a ferrous, means reduced form, it has a 6 valency. If it is a ferric, it will be having 5 valency. So 6 valency, how it is been occupied. Okay. So this is the iron. So the nitrogen of each pyrrole ring, it will be combined. Okay. Then the 4 is over. Then 5th will be the histidine group from the globin chain. Okay. And the 6th will be oxygen. Okay. So like that only all the 6 valencies of the iron are occupied. Correct. So 4 will be the nitrogen of this pyrrole ring. 5th will be then this is which group? Which one? Histidine contain which group? Imidazole group. So this is imidazole group. So nitrogen of this imidazole group will form a coordinate bond, and the 6th coordinate bond will be by the oxygen. Okay. So like that it is there, and that is only the how the hemoglobin is carrying the oxygen. Okay. Now why hemoglobin, why iron, we will see subsequently. Okay. So this is the structure of the heme. So iron and protoporphyrin ring. Protoporphyrin consists of 4 pyrrole ring A, B, C, D linked by the methylene bridges, and they have the side groups. Okay. And iron in ferrous form, 6 valencies. 4 valencies will be by the nitrogen from the pyrrole ring. 5th will be from the imidazole group of the histidine, and the 6th will be the oxygen. Okay. So it will bind to oxygen, and the oxygen will be carried from one place to the other. Second, it is about the globin part. So globin, we already know it is a protein part. So it contains 2 alpha chain, 2 beta chain. Correct. So composition, 141 amino acid in alpha chain. Okay. And it is present on the chromosome number 16. Okay. Now why it is important? Because there is mutation. So there is mutation, there will be problem. So you have to understand. The second is the beta chain, contain 146 amino acid. This is molecular weight. It is present on the 11th chromosome. Okay. Now each alpha and beta chain, they have this kind of amino acids, 141 alpha and 146 beta. Okay. So the heme hemoglobin, it is a tetramer. Okay, so 1 alpha, 1 beta, alpha 2, beta 2. So 4, and with each chain there is one heme group. So one hemoglobin molecules will contain how many heme protein? 4. Okay, because it is with each chain. Alpha 1 will have one hemoglobin, one heme. Beta 1 will have one. Alpha 2 will have one heme, and beta 2 will have. So it contains 4. So it is a tetra. Okay, so it is as well tetra. So like for example here, so this is alpha 1, alpha 2, and this is heme protein, and this is beta 1, beta 2, and this is heme. So this has been denoted. Okay, so this one is form a unit, and that's why it is a tetramer. So it contains 4 unit. Okay, and that's why it is classified under the quaternary structure. Okay. Now if you go a little bit in detail, so like that structure is there. Okay, so this is a kind of different view. So if you see, there is a heme which is there in each pocket. This is alpha chain. Here it is alpha chain. This is a heme pocket. This is a beta chain, heme pocket. This is a beta heme pocket. So like that structure will be there. Okay. Now if you see, so these are the helix. Correct? So these are the helix. If you see helix, these are the helix. These are the helix, helix, helix. Okay. So they have a different helices. They have classified A, B, C, D, E, F, G, and H. Okay. It has been classified like that. The alpha chain will have, there is a lack of D subunit. However, the D will be there in a beta. Okay. So this is the for your understanding. Why it is understanding is required? Because you understanding is required. See, the function of the hemoglobin is carrying oxygen. So where the oxygen is binding? In iron. Correct. So the question is simple. If the iron is carrying the oxygen, why this complex structure is required? Iron can easily, if the free iron is there in our blood, it can easily transport the oxygen. Why this complex structure, all these things are required? Because first important thing, iron is a metal. It has a, if the oxygen binds to the iron, it has a strong activity. It will causes Fenton reaction. It will causes formation of free radicals. One thing. Second thing, if it binds also to the iron, it will bind very tightly, so that it will not release the oxygen at the circulation. What function we require? It should take the oxygen from the lung. It should give the oxygen to the peripheral tissue. It should take the carbon dioxide. Should carry to the lungs. It should exhale. It should remove. So that is a function is required. So that much complex functions will be done only when this kind of structure it is there. The question should also arise, why there are amino acids can't transfer. Okay, so the amino acids, there is the same problem. If the oxygen binds to the amino acid, there is this unloading to the oxygen, it is difficult. Okay. So the complex structure of this hemoglobin is required so that it can pick up the oxygen from lungs, transport it, deliver the oxygen at the peripheral tissue, pick up the carbon dioxide and bring it. So that is the functions of this hemoglobin, and that is there. Now if you see in previous, the heme part where the oxygen is binding, it is present in the pocket. See, it is present in the pocket, it is not in the outside. It is in the pocket, and that is hydrophobic. Okay, it is a hydrophobic region where this is present in the pocket. So that inside only you will provide a proper environment. Correct. Outside it will be difficult. Inside only it will be proper environment, proper bond interaction, proper distance with the iron, oxygen, peripheral amino acids. They will form a proper interaction. So that only at the lungs it will take and the tissue it will deliver. Okay, so that is the main function of this to understand the structure. So this is the structure. So there are chains, there are helices A, B, C, D, A from to H, and in alpha this one is absent. Now here also one. So this is the the structure will be there. So this is your 4 pyrrole ring A, B, C, D. This is your iron, correct? So this is your heme part and this is your globin part. Okay. Now when the oxygen is coming, so as I told you, there are iron has 6 valencies. 4 will be by the pyrrole ring. Okay. 5th will be from this histidine, imidazole. Okay. Now as this is coming very close to this iron, it is called as a proximal histidine. Now, so what is proximal histidine? There is question, proximal histidine and distal histidine. Okay. So first to understand what is 87 and what is F18. Okay. So 87, how many amino acids are present in alpha chain? 141. Beta chain? So if you calculate 1, 2, 3, 4, 5, 6, 7, whatever 87 is there, that is the 87. Correct. Now F8. These also are classified into helices. Correct. Each helix has, so F helix 8 amino acid. So that is there. Okay. So this is called as a proximal helix. Huh? Histidine. HIS is histidine. This one. That is leucine. It is valid. That is between F and G there is some segment will be there. Okay, so that is there. Okay. So blue one, that is a proximal. Now if you see, there is another, skip quite, so another histidine which is present at 58. Now in a sequence, 58 will come first or 87 will come first? But why it is called as a distal? 58 is called as distal. So the reason is that it is far away from the iron. So that's why it's called as a distal. So though it is early 58, but as it is far away from the iron, because here only the oxygen will bind here. Okay. And here the oxygen will bind, and this oxygen will be there is interaction between this histidine and this oxygen. Okay. So that's why it's called as a distal histidine. However, 87, which comes later also, it is very close to the iron. That's why it's called as a proximal. Okay. Now see the structure. See the plane, the iron, because that is also important. Okay. Everyone is getting? So this is the proximal histidine. Though it is 87, it is proximal because it is close to the iron, close contact. And second histidine, which is present at 58 position, it is though it is a 58 early, it is called as a distal because it is far away from the iron. Okay. So these are the structural important things. Now once the oxygen is coming, it will bind here, this iron, it will form a 6 coordinate bond, and the O2, the other oxygen, it will bind to here, so that the interaction is proper and it is ready for the transport. Now a more complex, that first it has to bind also and then it has to deliver also. So both the interactions should take place properly. Okay. So to understand this thing, so this is the structure. Okay. So you know there is a heme part, you know there is a globin part. There are 4 groups, 4 chains, alpha 1, alpha 2, beta 2, beta 1, beta 2. Each will have one hemoglobin, which heme part. Okay. you know each alpha chain have a helices A to H. Alpha will have a D, there is absence of D, beta will have, and you know the ion, so you know the proximal histidine, you know the distal histidine, you know why it's called as the proximal, why it's called as a distal. Okay, so this one structure you know. Heme also you know, there are ion is there and there is protoporphyrin ring. On this ion only the oxygen is binding. Okay, so this much you know about the hemoglobin, the structure you know. Now the same similar structure is present in the myoglobin also. But in the myoglobin, it only contains one. Now we are first, let's finish with the structure. You know the structure of hemoglobin, 4. Now the myoglobin only one chain. How many chain? Myoglobin has one chain. So here also chain is there, but there is a protein part, that is globin, and heme part also is there. So protein part will contain 150 amino acid, is compact globin, and there are helices are there as we have discussed previously. The difference is that it doesn't have a more unit, it is only one unit. Okay, so structure you know. So same ion, this is the protoporphyrin ring and the other protein part. Okay, so in subsequently you will be understanding that heme, the protein part, the non-protein part, also called as a prosthetic group, it is present in many other enzymes also. Like for example, your cytochrome, they have heme part. Okay, catalase is you are having heme part. Hemoglobin is there, myoglobin, these are the classical example. Okay, so here hemoglobin and myoglobin, hemoproteins, so they, you know the structure. So the difference is there, myoglobin only one chain, one unit. Okay, hemoglobin 4 unit. Okay, now if I ask you how many oxygen molecule will be binding to the hemoglobin and myoglobin? Myoglobin 1, hemoglobin how come? 1 with the each, 1 oxygen with alpha 1, which is heme, which is there in the alpha 1, 1 with the alpha 2, 1 with the beta 1, and beta 1 and beta 2. Okay, so the 4. However, myoglobin only 1. Now what is the function? Now function of myoglobin is storage, because you are walking, talking, all the muscles which are there, it will be requiring oxygen. Okay, finally it is oxygen only, because how the oxygen? ATP production also you require oxygen. Okay, you will be understanding when you will understand the metabolism. So oxygen we are consuming. However, hemoglobin function is to transport. Okay, so storage is there in myoglobin. Myoglobin doesn't play important role in transport. Hemoglobin, it is a play important role in oxygen and carbon dioxide transport, and also it is a very, very important buffer, the imidazole group of histidine which is there. So if you see the sequence alpha and beta, there are about 36 histidine molecules are there. So you should understand the importance of histidine, and as because of there are histidine, it has a maximum buffering capacity. Okay, so functions you know now. Myoglobin will be working only for oxygen storage, hemoglobin will be for transport and buffering. Now our main task is that why the myoglobin doesn't transport and why hemoglobin doesn't as a storage. Okay, so that's only you will understand the structure and function relationship. Correct? So first understand the function of the hemoglobin properly. So lungs, so we will take the oxygen, and in the lungs the function of the hemoglobin is to take the oxygen and to deliver the oxygen at the tissues. So the concentration of oxygen is high in the lungs. That is called as a partial pressure of oxygen, PO2. Okay. So in the lungs it is more. So it is about 100 to 120 millimeter of mercury. In inspired air, the concentration of oxygen is around 128 millimeter of mercury. However, in the alveolar air, it is about 100. Okay. So once you are expelling the carbon dioxide, the concentration of carbon dioxide will be low. Correct? So that is only it means. So if you see the partial pressure of oxygen in arterial, we say about 100 millimeter. So like you must be knowing during COVID, there is a pulse oximeter is there. Okay. So it will measure your oxygen concentration in your arterial blood. So what you will do, you will just pick up and you will put it in your hand and you will wait. So after some few minutes, it will tell you how much partial pressure of oxygen is there. So that is there. So in arterial it is about 100 and in venous it is about 35 to 40 millimeters, so around 40 millimeter of mercury. Okay. Now what is important, that also you should understand. So the flow of oxygen will be along the concentration gradient. So from high concentration to the low concentration. Correct? Correct or not? So outside 180, 128, in the lungs it is about 100, in the peripheral tissue it is about 40. So the situation is like that, or environment like that, the oxygen flow inside the tissue from lungs. Okay. So that is the importance of this partial pressure of oxygen. So the oxygen will bind to the hemoglobin, heme part, to form oxygenation. It is oxidized and it is binding to the ferrous form of the hemoglobin. It is a non-enzymatic loosely and it is a reversible. So this reversible is also important, and that is only it can take the oxygen, it can deliver to the wherever it is required. Okay. So hemoglobin in the lungs, it is about 97% saturated with the oxygen, and that is called as the oxyhemoglobin. Okay. Now we are talking about allosteric. So what is meant by allosteric modification? Yes. So one is the other than active site, the modulation takes place. Then another, what is the important thing? It can be activated, it can be inhibited also. Another important thing. The most important thing, yes, it doesn't follow the Michaelis-Menten equation. So why it doesn't follow the Michaelis-Menten equation? What is the main important thing? The main important thing that time also is discussed. So how you describe, how you distinguish the allosteric inhibitor and the non-competitive inhibitor? Yes? Reversible. Okay. Any other? Which will causes the conformational modification, structural modification. So that is the important thing. That day also we have emphasized. Allosteric modulator, whether it is activator or inhibitor, it will causes structural modification, conformational changes. Okay. And that only is important, and that only will determine whether it is inhibitor or activator. Okay. So that is only the important distinguishing characteristic about the allosteric and the other kind of regulations or other kind of this thing. Okay. So why I am telling this thing? Now you consider heme as a kind of enzyme and oxygen is considered as a substrate. Okay. So once the oxygen is binding, there is an alteration in the oxygen, in the hemoglobin. So that is called as a homotropic. There is also homotropic modulation and heterotropic modulation. Homotropic modulation means what? Substrate and modulator is same. Heterotropic, substrate and modulator are different. So here also oxygen, if we bind to the hemoglobin, it will cause structural changes. That what is that we will see. That's why oxygen, it is acting as a modulator also and it is acting as a substrate also. If you consider in enzyme substrate in way. Okay. Now if it is oxyhemoglobin, there will be deoxyhemoglobin also. Correct? So on the resting it is about 75% saturated. So in outside it is about 75%. So each gram of hemoglobin will bind around 1.34 ml of oxygen. And how much hemoglobin is present in our body? 14 to 16 gram per deciliter. So how much it come in ml? 1.34 into 15 if you consider. So 20 around. Okay. So 20 ml will be carried by the 100 ml of blood. Okay. So that much is there. Now the point to be emphasized is there are two forms of the hemoglobin. One is oxyhemoglobin and another is a deoxyhemoglobin. Okay. So in the deoxyhemoglobin, oxygen will not be there. In oxyhemoglobin, oxygen will be there. Okay. Okay. Second, unloading. It should be done at the peripheral tissue where partial pressure of carbon dioxide is more and there is a partial pressure of oxygen, it will be less. There is a 40 millimeter of mercury. Okay. And that is called as a cooperative binding, or we have understand the positive modulator, positive allosteric modulator. Now hemoglobin, 4 unit, alpha 1, alpha 2, beta 1, beta 2. Each will have one heme. Okay. So and each hemoglobin will bind to the 4 oxygen molecule. Now why it's called as a cooperative binding? Okay. So 4 is there. So first one molecule will come, oxygen. It will go and it will bind to the any one subunit of this thing heme. So because of this binding, there is a structural changes will be happening. So what these structural changes, that will keep it aside. Because of something it will happen, and because of that changes, the affinity for the alpha 2, beta 1 and beta 2 is increased. Okay. And that's why oxygen will bind tightly with the hemoglobin, so that, and this is all where it is happening in the lungs. Okay, it is happening in the lungs. So that is there. So due to the tetrameric structure of hemoglobin, oxygen binding doesn't happen simultaneously. So it will happen first oxygen to the first subunit, which will enhances the binding of further oxygen to the remaining subunit, and that is because of the greater affinity. Okay. And because of that one, they have the sigmoidal kind of oxygen dissociation curve. Usually, if you consider hemoglobin as an enzyme and oxygen as a substrate, what is that? Usually the hyperbolic curve will be there, correct? Ideally. But because the oxygen is having a cooperative binding, this hyperbolic curve is not there. This is a sigmoidal curve. Okay. So initially only the affinity will be less first, but once the first molecule bind to the one unit, affinity for the remaining subunit is increased, and the oxygen will bind very tightly, and it can bind easily and can go further. Okay. So that is the meaning of that one. So three modifications, three structural changes are happening. Okay. So these three structural changes we will see. So the first structural change is the protoporphyrin is a ring and all four are present in one plane. Okay, and the ion will be there inside, but sometimes it will come outward, sometimes it will come in the plane, sometimes it will come out of the plane, and that also it is determining the one of the structural changes happening. So once the oxygen is bind to the ion will be drawn in the plane of porphyrin ring. So usually the ion is present like outside, little bit. But once oxygen binds, it will go in the same plane. So this is the first structural changes happen. Second change is the rotation. Now 4 unit, alpha 1, alpha 2, beta 1, beta 2. Now alpha 1 and beta 2 and alpha 2 and beta 1, they have the two plane. So there is a tilt happen. Okay, I will show you in the diagram how this tilt happen. So this tilt is about 15 degree. Okay, so this 15 degree. So this is the second changes is happening, and on this second another change, all this happens is because of the breakage of the salt bridges. Okay, now globin, amino acids, each amino acids has side chain R group, amino group, carboxylic group. So all these they form interaction. They will form the salt bridges. These are the non-covalent interactions, so that the stability, the hemoglobin will be stabilized. Okay. So once oxygen binds, these bridges are broken, and subsequently the oxygen will be binding properly. Okay. So this is the three modification. These three structural changes happens. So the first is about the movement of ion. Okay, so if you see here, this oxygen, this ion is little bit outside here. Okay, but once the oxygen binds, you see the distance. It is like a similar distance. Okay, so it is coming in the one plane. So first structural change. Second structural change is the tilt. Alpha 1, beta 2, and this one, they will be a little tilt will be there. So this tilt will be there. This tilt is about 15 degrees Celsius, 15 degree, not Celsius, this 15 degree, okay. So this is the second structural change, yeah, anyone? So this is the second structural changes happens. And the third is about the breakage of salt bridge. So consider diagrammatically. So once this oxygen binds to the alpha 1, there is a, see, these salt bridges which are there, it is broken down. Second, again it is broken down, and because of that it has a more affinity. So like that, all the salt bridges which are there in between, it is broken down, and it is a fully oxygenated state. Okay, so oxyhemoglobin is called as R. We'll discuss what is R. And deoxyhemoglobin is called as a T. T stand for tense, R stand for relax. Okay, so that is the why tense. This because of the salt bridges it is tense. Okay, once the salt bridges are broken, it is a relax. Okay, so these three modifications takes place in the hemoglobin so that it will bind. Okay, now so that we will understand when they are in the lungs. Okay, now what is happening when they are in the tissues also, so that also we will see. So any doubt about this unloading, what is meant by cooperative binding? So this cooperative binding, cooperative modifications will be explained by the Hill's equation. Okay, H-I-L-L equation. So Hill equation, they have explained this cooperative binding. Now there are two forms which I have discussed. There is a T form and there is a R form. T stand for tense, R form relax. So T is standing for the deoxyhemoglobin, R stand for the oxyhemoglobin. So deoxyhemoglobin, it will bind to the carbon dioxide, hydrogen and 2,3 biphosphoglycerate. However, oxygen only binds to the oxygen. So there are various salt bridges are there. However, in R form, salt bridges are broken down. It is a more constrained, it is more tense form, so that's why T. It is a less constrained. 2,3-BPG is centrally located in the T form. So if the 2,3-BPG is there, it will favors the T form. T form stands for deoxyhemoglobin. Clinical significance I will tell. However, in here it is not able to bind. It is removed from this R form. T form has a low affinity for oxygen. However, R form has a high affinity towards oxygen. T form predominates when there is a low partial pressure of oxygen. R form predominates when there is a high pressure. So, if I ask you which form is formed in the lung, R form, because the oxygen concentration is high. And which form of hemoglobin is formed in the tissues? T form. Okay. Now, because of this modification only, hemoglobin can take up the oxygen from the lungs and can deliver it safely to the peripheral tissue. Okay. So that is important. So the relationship between the oxygen, hemoglobin and oxygen, so that it will deliver the oxygen in the peripheral tissue and take up the oxygen in the lungs. This is been mentioned by this oxygen dissociation curve. Okay, and this is how you will be coming across what are the causes for the right shift of the oxygen dissociation curve, what are the causes for the left shift of the oxygen dissociation curve. That will be taken care by the physiology. Okay. So one important thing about now we will see about the tissues. Okay. So we will see at the tissue. So what concentration will be high in the tissue? Carbon dioxide. Okay. Now carbon dioxide, it is transferred by the three ways. First is a dissolve. Little bit it is dissolved in the plasma. How it is dissolved? So once carbon dioxide plus water will form carbonic acid. It will be dissociated into bicarbonate and ion, H plus ion. H plus ion will lowers the acidity because it is a negative logarithm. So you have to keep it in mind. Okay. So pH will be low when the H plus ion concentration is high. It is a negative logarithm, correct? So because of the pH, we can't allow this tin to happen. So whatever the other mechanism, it will reduce. So this is the one. It is constituted about 15% of oxygen, carbon dioxide transfer. Second, 75% is by this hemoglobin. Okay, that is called as an isohydric transport. And third, 10% it will be by the carbamine. So carbon dioxide will directly bind to the hemoglobin. Okay, amino acids, and then it will be transported. So that is a 15. That is 10%. Maximum is a 75%. So we are talking about this 75% where there is no change in the pH. That is called as isohydric. Okay. So what is happening in the tissue? Carbon dioxide will be taken by this is RBC. There is an enzyme carbonic anhydrase will convert into carbon dioxide, carbonic acid. It will be dissociated by carbonate and H plus ion. And this H plus ion will be binding by this hemoglobin. So that's why it's called as a buffering capacity. Okay, it is play important role in the buffer. So it buffer. So because of this H plus ion, whatever the oxygen it has carried, it is delivered to the peripheral tissue. So carbon dioxide is also taken and oxygen also is delivered. So that is only the function you wanted. Now as I told you, so in the lungs, 4 units. So once the oxygen binds to the 1 unit, it increases the affinity for the remaining. Now in the peripheral tissue, what is happening? When H plus ion binds to the 1 unit, structural changes will happen and the oxygen affinity for the other, it will be reduced. So the oxygen is delivered properly in the peripheral tissue. Opposite same thing is happening in the lungs. So once oxygen binds, increase affinity, bind oxygen. In peripheral tissue, one hydrogen binds, oxygen affinity reduce, deliver the oxygen. So that is not the function, it can take up the oxygen, deliver it. Okay. So this is deliver. Now bicarbonate is there. So bicarbonate, it will be released in the circulation. With the exchange, it will be, the chloride will be taken, and that is called as a chloride shift. Okay. So this is the chloride shift which is important. And this is how the oxygenation and deoxygenation takes place. Okay. So this is happening in the lungs and this is happening in the tissue. So that we will see in next lecture. No need to hurry. Okay. So slides are there here. There is no need to take print and this thing. You understand what is happening and then you can able to. Okay. Yeah. Thank you.